thank you for this opportunity to talk about this 99% Accuracy Club and possibly make the world a better place. That's my goal. So the 99% Accuracy Club is the title of my talk, but I could have added a subtitle, why you don't want to become a member. So accuracy in this context is a familiar measure of performance of a classifier that I guess you have all been dealing with, at least if you're in like machine learning field. That is just one measure that you can use. Other measures are, for example, the AUC, the area under the receiver operating curve. But this is not very important in this talk, which measure you are using. So it's not about picking the right measure. Every measure has the same inherent problem that I will get to. So when we talk about accuracy of classifiers, it's easy to see that the machine learning has had great success in developing classifiers, and there's still a big potential. So the accuracy or the performance of classifiers is quite an important field in research and development as well, and for a better world. When we measure the performance of the classifier or several classifiers on the same task or the same problem, we end up with something that we like to call state of the art. And this is, as I guess you know, this is the best performing classifier on that task or that problem. And the state of the art, of course, depends on the difficulty of the task. So you can have a state of the art which is much closer to 100% accuracy on one task, but much lower on another one. And the reason why this state of the art is so important is that in many aspects it sets a lower threshold. It sets a lower threshold for publications. So if you have developed a new classifier and the performance of your classifier is above the state of the art, you will get published. If not, you will not get published. It's also sets a threshold for funding and of course for implementation in the real world. So if you're going to choose a classifier to solve a problem, of course you want to choose the best one. And it also measures kind of when a problem is solved. So, and of course, if you have a 99% accuracy, you can say more or less this problem is solved. So we are all kind of aiming for that 99% accuracy as a community. But I will try to convince you why you don't want to be there necessarily. And I will do that through an example from a Kaggle competition. And I guess many of you at least are familiar with Kaggle. Started in 2017 and has launched a lot of machine learning competitions where a host provides a data set and prize money. And then normally everyone can form a team and compete. And if you perform the best, if you have the highest accuracy or AUC, you get the prize money, which is nice. And this has made quite an impact, especially for neural networks and also other things. So in 2020 was a melanoma classification challenge, and the first prize was $10,000, which is not uncommon in Kaggle. But before I talk about that, I will launch the 2022 coin flip classification challenge, and I want all of you to participate in this one. Okay, now there's only one participant left, finally, and I can declare a winner. Don't know his name though. The probability of guessing if the true performance of your classifier is like flipping a coin, 0.5, then the probability of guessing correctly, so 4 times in a row, is about 6%. So this is quite impressive. And we will see how this plays out in a bigger challenge with 3,300 participants. So, challenge over, I will share my screen. So this 2020 melanoma challenge hosted by Kaggle, just give you some context, there were about 3,000 teams and about, I think, 30,000 images. And there are only 2 classes. It's melanoma, it's a form of skin cancer. It's rare, it's fatal, it's difficult to detect. And of course, by launching this challenge, we kind of hope that machine learning could improve classification and save lives. And as you do when you train a model, especially within machine learning, you should always do this, is that you have a training set where your parameters are fitted to the data. You have a validation set where you perhaps set some hyperparameters or you stop training. And then you have an independent test set, a test set that you never see during training and validation and developing of this method. And this is how Kaggle explains it. You train your model on your training set, you evaluate the model on your validation set, and then you tweak the model. And you keep tweaking and tweaking and tweaking. And finally, you pick the model that does best on the validation set, and you confirm the results on the test set. Let's see how that played out. In this competition with 33,000 images in the training set and 7,500 in the test set. So like a fairly good amount of images, you could say. And the teams, the 3,000 teams, was ranked according to their performance measured by this receiver operating curve that I guess you have seen before. And we want, of course, to have as many true positives as possible, detecting the cancer, and as few false positives as possible. And the line in the middle here, that's what you would get if you just tossed a coin or flipped a coin in any challenge. So we want it at least to be better than 50%. So the area under that curve is our measure of performance. So anything under 50% is like tossing a coin. And if it's close to 100%, then we get everything right. Okay, so this is what Kaggle calls a public leaderboard. So you get the train set, and then to validate your model and to stop training and tweak your hyperparameters, there's this validation set, and the results are public, so you can all the time compare your own performance to the other teams. And that's why it's called a public leaderboard. And we see here that on top of the public leaderboard is a person who had a score of 99%, and he spent 276 tweaks to fit his model to the data. So he kept resubmitting his model to the validation data, and got better and better results. And at 99%, he stopped. And we see that we have quite impressive performance here. And this is what happens when you reuse your validation set, or if you reuse your test set. You might think that your test set is independent, but it's only independent. It stops being independent if you use it once. So you can only use a test set once. And this kind of shows what happens. You get very, very, very good performance. And of course, what Kaggle does, which is brilliant, is that they keep their test set to themselves. No one has access to the test set. So all models here, all classifiers, are tested only once. You cannot tweak your model to the performance of the test set. So, but from this public leaderboard, you could assume that the state of the art for melanoma classification was 99%. So what happens then when these models are used on an independent test set? This is what the Kaggle calls a private leaderboard. So what happens here is that the performance drops dramatically. So the best performance from the validation set was 99%, and the best performance from the test set is 95%. That's quite dramatic when we're talking about state of the art. What we also see, that we can see from this, the green numbers here on the left, is that these are the rankings from the validation set. So these people, they did not try to be the best team on the validation set. They stopped training, they stopped tweaking their models, they stopped overfitting, and their ranking went from 880 to 1. This, I think, is familiar for very many of you. We know that the test set should be independent. But if you review papers, you see that a lot of people do not follow this this standard of having an independent test set. And it's a big problem if the overall community believes that the state of the art is 99 when it in fact is 94 or 95. But I will try now and convince you that 95% in this context is also an overfitting or an overestimation of the performance. This is not the state of the art. The state of the art is much lower than 95. And then I ask you to kind of try and keep in mind this coin flipping challenge that I launched, that when you do have a lot of teams that compete together, then the best performing team will always be an overestimation of the true performance abilities. So let's have a look at that. This is just another, so here you just see like the top 10 or the top 7 entries or the rankings, but there were like 3,300 teams. So let's see how they perform all together. This is called a violin plot. And it's just on the y-axis here, you have the AUC from 0.2 to 1. And you have the teams and their validation score to the left, and their test score to the right. And you can see that most validation AUCs they're pretty high compared to the test. I think it's actually about 1/3 of the validation scores are above the highest test score. So apparently a lot of people are overfitting here. And interestingly also is that people know this. If you look at the team names, so those from the top 10 validation set performance, you see here number 3, they have called themselves best overfitting, and number 5 have called themselves overfitting. So people are very well aware of this, but keep doing it. Don't know why. So if we zoom in on those that have a test score above 80%, it seems like, so the shape of these two plots are pretty similar. So more or less all teams overfitted their model to the validation set. More or less all teams. Also the best performing team did that. Or we have a reason to believe that they did that. But now, why is 95%, so the best performing team, why is that also, or an AUC of 95, why is that also an overestimation of the state of the art? So since I'm a statistician, I'm going to talk a bit about uncertainty and how we measure that, and how I think more people should measure uncertainty in more of what they do. So if you have the true performance of AUC of 0.95, then for this data set or a similar data set, you will have an uncertainty. So if my true performance is 0.95, then my AUC will be somewhere between 0.94 and 0.96 in most of the occasions. Because if I had a different test set, I would have a different performance. So this performance would be connected, of course, to my true performance, my true underlying performance. So what happens if I could have just run this competition over and over again, getting new test sets and new test sets? And this is how the best performing team, we could believe that they would perform, somewhere between 94 and 96. But remember that this is the best performing team among 3,000 teams. So as I was trying to estimate your abilities to classify or to guess a coin flip, and if I only pick the best one, we should assume that the best one is on the very far right of this confidence interval. So we need to move our confidence interval a bit. We move it so that the upper limit of the confidence interval is the best performing team. And then we go from 95 as the state of the art and to 93.5, more or less. And we go down, and the team who performed 93.5, they are already ranked as number 427. So you cannot really distinguish the performance of these two classifiers. They are equally good if you take into account that there's some uncertainty here. that, of course, team number one, they performed on this specific data set, they performed best. But if we would have given them a new data set, it could be team number 427. So it's kind of arbitrary who gets this $10,000 prize money. But then within this confidence interval, this red confidence interval, now we have more than 1,000 teams. And the 95% confidence interval is not supposed to cover all variability, but only 95% of it. So we want to move this confidence interval further down. So we only cover 95% of the variability. And we move it, the upper limit down to rank team, the team that is ranked as 34. And now our new estimate for the state of the art goes from 0.95 to 0.93. And keep in mind that on the lower end here at the confidence interval, you see another number, 0.91. What does this mean? It means that if you were one of the competitors in this challenge and you were ranked number 1,566, your classifier might be just as good as the one team who was ranked number one, just because the independent test set is a bit arbitrary. In the same way as if we would do the coin flipping challenge once more, we would not have the same winner, or probably not have the same winner. So when opening a competition, keeping the independent test set to yourself, we solve this problem of extreme overfitting that we can see. People try to publish with 99% accuracy. And if I'm the reviewer, I stop it. But these competitions with thousands and thousands of teams also overestimate the state of the art. And it's impossible to beat if you don't have a fair amount of luck. Also, of course, you need a good classifier, but then you need to have a fair amount of luck. So what I hope maybe I have, I don't know if I can convince you, but maybe this will be just something you can think a little bit about. So if we have people reusing their test set, not a truly independent test set, we get a state of the art of 0.99, which is way too high. It's not realistic at all. So their classifier will not perform this good when given an independent test set. Then we have the highest ranked team. Their state of the art is also inflated. It's too high. They will not perform at 0.95 if they were giving a new test set, because they were just the lucky ones among those 1,500 best performing teams, 1,500 teams that performed very similar. So the best estimate for the true state of the art from this challenge is actually 0.93. So we go from 0.99 via 0.95 and down to 0.93. That's quite a lot. And remember that if your classifier performs at 0.91, you're still within this uncertainty or the variation that just the random sampling of a data set will give you. So this is the problem. If if we pretend that the state of the art is 99 or even 95. But of course, it's easy to point at problems. So the big question is there any solution? Yes. If you are a reviewer or an editor, be very demanding when it comes to independent test sets. Very, very demanding. And please start asking for confidence intervals. This will tell you a lot as a reader, also about the test set itself. Is it a good test set? If the confidence intervals are very wide, then it might not be a very good test set. And if you're a host, if you're hosting a Kaggle competition, you can simply bootstrap the test set, and you will automatically get out of it some measure of uncertainty, and you don't give away the $10,000 just to the team that was the most lucky among the 1,500 brilliant classifiers that were submitted to this challenge. So back to the training and validation and test sets. So bootstrapping is just that you resample from a test, from a data set, so that you get some variation from bootstrap to bootstrap. Because of these 7,500 images that was in the test set for this challenge, it's not these exact images that are interesting for a classifier. You want to use them on new images. But this test data set is very static. But if you bootstrap, you just resample from your data set, then you get a set that is less static, and you can measure the variability or how a classifier's performance varies when the data set varies, as it would out in the real world. You want to bootstrap also if you are developing a method in your validation set, because then you avoid overfitting. And if you avoid overfitting, you will have a better model. Overfitting creates the worst model. So if you compete in a competition, or whatever you do, if you overfit, if it's seemingly very good, then in reality it's bad. And of course you could bootstrap on the train set as well, but then it will the convergence will be very, very slow. But more importantly, bootstrap the test set, because then you will get a much better estimate of the true performance of your classifier. The true performance, how will your classifier perform on yet another test set? You get a pretty good measure of uncertainty, and this measure of uncertainty gives you a meaningful way to compare models. Because if one model has an AUC of 0.9137 and the other one has 0.9138, it's not really because of differences in the abilities of the classifiers to classify correctly. And this measure of uncertainty will tell you how far is the distance between two classifiers. So please bootstrap your validation set, bootstrap your test set. I could, of course, instead say more data, have multiple test sets, but that is not a solution to anything. That's more like wishful thinking. And this will cost you, if you haven't done it before, it will cost you like maybe 5 lines of code, and then, of course, a little bit of time, but it will definitely be worth it. Then you can maybe get those $10,000 if you enter a Kaggle competition, but you can yourself be certain that when I submit this paper and declare to the world that this is the performance of my classifier, it is the true performance. Thank you. This is just the websites and the GitHub with the code for calculating the confidence interval. And thank you to Andrew Marchak, who's here today, for web scraping.